Right, as you can see from the title, this lesson is all about balancing chemical equations. I'm going to try and start off relatively straightforward in terms of looking at chemical formulae and compounds, and also then try and go through how to balance an equation, get you guys doing some practice, and then finish up with some really quite advanced methodology. Right, so first up, we just need to make sure that you've got a good understanding of chemical formulae and what they mean. So you can see you've got some chemical formulae on the left-hand side there, some relatively common compounds. Just check that you know them all. So the first one's water. Second one you probably know is sodium chloride. Then you've got calcium carbonate. You might recognise the fourth one down, H2SO4, as being sulfuric acid. Then you've got magnesium hydroxide, calcium nitrate, and ammonium carbonate. All I want you to do though is to tell me the number of atoms and the names of the elements. Obviously you can use a periodic table if you wish, because you have to learn those names. This is all about making sure that you've got the numbering situation sorted out. Just a little heads up, this always crops up. The second one, and also throughout this particular presentation, that is a capital C and a lower L, therefore it is chlorine, Cl, not Ci. So this slide just has the answer to the first one on there. I'm sure probably you're pretty clear about this, but just to clarify. So we have two hydrogen atoms. Remember, capital letter tells you the chemical symbol. The lowercase small number comes after the chemical symbol. That tells you how many of that atom there are. So there are two atoms of hydrogen. If there is no number, that means there's only one, so there is one atom of oxygen. And just to be clear, that whole thing, atoms joined together, would be called a molecule. All right, and because they are different, H and O, that is a compound. If they'd been the same, it would have been an element, but of course these are all compounds because they all contain different atoms. Just a few other little things before you look at the next slide, which has got the answers on. If you have brackets, then that means it's the number outside the bracket times everything in the bracket, just like in maths. And here again, down here in the calcium nitrate, you'd have to multiply those numbers to get the amount of oxygen atoms. So when you think you're done, have a look at the next slide for the answers. Okay, here's your answer slide. Hopefully everything on there is okay. Like I said just now, just be careful about brackets. So you've got one copper, capital C, lower U, and then obviously the brackets. So this thing in here is nitrate, so there's one N there. So you do N times 2 to get you 2 nitrogen, and then there's 3 oxygen atoms. So 2 times 3 gives you 6 in total. Similar thing with the ammonium carbonate underneath. Okay, another little thing just to check before we get into the actual balancing equations. If you have a chemical reaction, of course, the substances at the start called the reactants, and the reaction occurs, and then you have products at the end. I would just like you to pause this and decide which of those 4 statements is correct. Okay, so the answer was B. The mass of reactants is always equal to the mass of products. That's, of course, because in a chemical reaction, all you're doing is rearranging those atoms from the reactant molecules and forming new molecules, right? So the total number of atoms at the beginning and the end is always the same. Therefore, the mass is always going to be the same. So if the mass doesn't change in a chemical reaction, there must be the same amount of atoms before and after a chemical reaction. So how does this equation work then? So this is the reaction between hydrogen and oxygen. You probably know this as the squeaky pop, and it will form water. But if you have a look here, you've got a bit of a problem, because there are 2 hydrogen atoms on the left, 2 on the right, but 2 oxygen atoms on the left and only 1 on the right. So what's happened to that other oxygen atom? Well, what that equation tells you is what reactants are needed, hydrogen and oxygen, and what the product is, water. What it does not tell you at this point is the amount of each that is required or formed. So what you then have to do is to work out the amount of each that is required or formed. And I'm going to show you how to do that on the next few slides. Right, so how to balance an chemical equation. The Mr. Foyle method, that's written there just because you may well have been taught different ways of doing this. You won't see this method like in a textbook or anything. This is something I've come up with. So it works every time though, so this is how I'm going to show you how to do it. Okay, so I'm going to show you a set of rules on how to balance an equation, and after I've been through them, we're then going to look at applying them to this particular reaction. So first up, you need to count the different atoms of each element on each side of the arrow. So in this case, you'd be counting the atoms of hydrogen and oxygen on both sides. If they are not the same, write the exact same formula of the substance with the smaller number of atoms underneath, and then count everything again. And continue doing this until every element has the same number of atoms on each side. So you'd be looking for the same number of hydrogen and oxygen on each side in this case. And then rewrite the equation with the number of each substance written before it using large numbers. Right, if that's not clear, I will show you shortly what I mean by that. So, starting with the hydrogen atoms. There are 2 hydrogens on the left-hand side. Now move on to the right-hand side, and you can see that there are 2 hydrogens on the right-hand side. Then we're going to move on to the oxygen. And if you look at the oxygen, you can see there are 2 on the left-hand side. And if you look at the right-hand side, you can see that there is only 1. Right, so what do we do about this? Well, what we don't do is write a little 2 there, because that would change the chemical formula to H2O2, which is not what is formed in this reaction. Right, what you do is you write the formula underneath and count again. So we're going to write H2O under here and count everything again. So there we go, we've written H2O underneath and we're counting everything again, and you can see we now have still 2 hydrogens on the left. But now you can see we've got 2 and another 2, so we've got 4 hydrogen atoms on the right. Okay, so these are now not the same. So what you do, you write the formula underneath and count again. So we're going to be writing H2 underneath and counting everything again. So now the H2 is written underneath, and you can see we've now got a total of 4 H atoms on the left. And if you count the hydrogen on the right, you can see there are also 4 on the right. Now, I know it seems a bit tedious, but we do have to count the oxygen again as well. So there are now 2 oxygen atoms on the left. And you can see with those 2 water molecules, we now have 2 oxygen atoms on the right. So everything is now balanced. Now, the final part of this is how do you actually write that? Well, you have to rewrite with numbers in front to show how many of each substance you have. So we now have 2 hydrogen molecules, so H2 and H2, 1 oxygen molecule and 2 water molecules. So to show that, what you're going to do is write a big 2 to show you have 2 hydrogen molecules and a big 2 to show you have 2 water molecules. And in terms of how you're describing that, 2 molecules of hydrogen react with 1 molecule of oxygen to make 2 molecules of water. Okay, so here's a second example. I'm going to run through it slowly like I did with the previous one. If you want to have a go at just balancing it yourself, go for it, but I am going to run through this one slowly like before. So you start counting with the nitrogen atoms. Right, you can see there are 2 nitrogen atoms on the left. And currently there's only 1 nitrogen atom on the right. So what we need to do is to write the formula underneath. In this case it's the NH3, and count everything again. So there's the NH3 written underneath. And you can see there are 2 nitrogens on the left. And now there are 2 on the right. So they're now okay. So move on to the hydrogen. So if we move on to the hydrogen atom, so there are 2 hydrogens on the left. But there are 6 hydrogen atoms on the right. So what do? You write the formula underneath the H2 to get some more hydrogens. Right, in this particular case then, if you write H2 underneath, you can see we've now got 4 on the left. But there are still 6 on the right. So you've got to do it again, write the formula underneath and count again. Now we've got 2, 4, 6 on the left. We've got 3, 6 on the right. The equation is now balanced. So how do we write that? Well, we've got 1 N2, 3 H2s and 2 NH3s. So you need to put your big numbers in front and you should have N2 plus 3 H2 makes 2 NH3, which you would describe as 1 molecule of nitrogen reacts with 3 molecules of hydrogen to make 2 molecules of ammonia, and ammonia is that NH3. Okay, on the next slide we have some practice problems for you to have a go at. Okay, so these are the answers to the practice questions. Just a couple of things which are common errors. First up, I did remind you earlier on, but just be careful about the stupid font I've used. So this is NaCl, not C capital I. All right, so just be careful about that. Things get a bit tricky kind of from 6 onwards, I guess. So I don't know really, if you just have a look, I guess just be careful about the bracket situation. So that sometimes gets people there. If you've got any multiples, by the way, that's fine. So what I mean by that is if, like, for example, for number, I don't know, 5, you wrote 2Mg plus 4HCl makes 2MgCl plus 2H2. That is absolutely fine because these things are just ratios. I would now suggest that you have a look at the balancing equations worksheet before you go on to the next slides. Okay, so we're going to have a look at some advanced techniques now for balancing equations. We're going to be looking at combustion reactions in particular, but the theory applies to other equations as well. So first of all, we'll look at a relatively simple example, and then we'll apply it to some more complex ones. So this is the reaction between CH4, which is something called methane, and combustion means burning. So when you burn CH4, you get CO2 and H2O, carbon dioxide and water. Right. So the point here is that all of the carbon atoms in the methane, the CH4, have only gone into making one product. Yeah, there's no carbon anywhere else, and there's no carbon anywhere else here. So what that means is, if you've got one carbon atom here and one carbon atom here, whatever I've got in front of this as my big number will always be the same as what goes in front of here, because there's nothing else that contains carbon. So in this particular case, I could just say, okay, well, there's a 1 in front of both of those. Fine. Right, the hydrogen from this CH4, right, all of that has gone into making water. It hasn't gone anywhere else either. So if you think about what that means, it means that the number in front of the water must be half the number of hydrogens in CH4. Why have I said that? Well, because each water molecule contains 2 hydrogens. So if I want, so I'm going to need 4, aren't I, for this one? So if I want 4, I need 2 molecules of water, because 2 times 2 will give me that 4. Right, now the reason that we're going to do that is because oxygen appears in 3 different places. So therefore we'll do the oxygen last. So if we've got a 1 in front of the carbon dioxide from the first point, second point, we've got 2 in front of the water. That means that I now have a total of 2, 3, 4 oxygen atoms on the right hand side. Now obviously I'm going to need a total of 4 on the left hand side. So to get a total of 4, I take that number and I half it. Why do I half it? Well, because the oxygen molecule is O2. So therefore 4 divided by 2 gives you 2. So the balanced equation is CH4 plus 2O2 goes to CO2 plus 2H2O. Right, now I appreciate that's pretty easy and you probably could have done that anyway without any of that chit-chat. But when we apply it to some slightly more complex examples, it really does become useful. Right, okay, a slightly more complex example. Let's have a look at this one, C3H8, some propane, let's burn that. Once again, all of the carbon has gone into making carbon dioxide, but this time we've got 3 carbon atoms on the left. Now they're only going here, carbon dioxide only contains 1, so basically whatever the number is there will go in front here. So I'm going to be putting a 3 in front of my CO2. Once again, the hydrogen has all gone to make water, and once again, water still does contain 2 hydrogen atoms. So whatever my number is here, I'm going to be halving it and put it in front of the water. So in this case, 8 divided by 2 is 4. And once again, I'm going to be counting up my oxygens and then halving it and putting that number in front of the O2. So 4 plus 2 times 3, so 4 plus 6 gives 10. 10 over 2 is 5, so a 5 in front of the O2. So this one would be 5O2, 3CO2 and 4H2O. Now I appreciate again that you may well have been able to do that one relatively swiftly anyway, but you can appreciate that as things get more complex, this becomes more useful. Right, this one's a little bit more complex, but it does introduce another little point. So there's another combustion. This one is something called butane, 4 carbon atoms. So once again, if there's 4 carbon atoms in butane, you're going to be putting a 4 in front of the CO2. If there's 10 hydrogen atoms in butane, you're going to be putting a 5 in front of the H2O. However, this does throw up a slight problem, because if you then count up your total number of oxygens, we have 2 times 4, which is 8, plus 5, which is 13. Now, 13, to get 13 oxygens, that's going to be a problem with O2. However, right, we can literally just half that number, which of course gives 6.5. That might make you a bit worried, because I hope you fully appreciate you're not going to have half an O2 molecule reacting, but the point here is this is just a ratio. So that means it's perfectly acceptable to write fractions to balance equations. So therefore you would get an answer of 6.5 O2, 4 CO2, 5 H2O. Now, because it is a ratio, you could also have written that as 2 C4H10 plus 13 O2 makes 8 CO2 plus 10 H2O. But I'm just telling you that when you're doing these combustion equations and you're using this quick method of that 4 goes there, half that, put it there, add the oxygens and divide by 2, it's still absolutely fine. Okay, so now there's some combustion reactions for you to have a go at on the next slide. Okay, answers to those combustion equations. I think I've checked them correctly, but do let me know if you think I've got any wrong. Couple of little pointers. They were not mistypes. What I mean by that is sometimes I've subtly changed some of these little numbers just to try and throw you out. Some of these were supposed to be carbon dioxide, some were supposed to be carbon monoxide, so that would be incomplete combustion, so just be careful about that. Coming down sort of for 7 and onwards, so 7, I was just being annoying really. This is an alternative way of writing out the formula, so writing out what's called a structural formula, so showing everything exactly the same, which is a bit more tedious, sorry about that. Then 8, 9 and 10 are using some compounds that also contain oxygen. So this is something called propanol, it's an alcohol. Right, you do it exactly the same way. However, they tend to trip people up because when you get your oxygen count, you've got to remember to remove one of them before you divide by 2. So a common mistake would be to put a 5 there. Similarly with number 9, you've got to take one oxygen off before you divide by 2. And in number 10, this is something called a carboxylic acid. What you have to do there is remove 2 of the oxygens before you divide by 2. Right, this particular slide is just for those people who are really into the kind of algebraic stuff and into solving these things using a little bit of algebra. So this is how you can do that. So here's another combustion equation. What you're going to do to solve it algebraically is use letters for unknowns like you do in normal algebra. So you would then put an A and a B and a C and a D and whatever, or X's and Y's, in front of each of your substances. Then you write out your algebraic equations. What I mean by that is you say, well, okay, if I look at carbon atoms first of all, there are 4 times whatever A is on the left-hand side, so 4A, and on the right-hand side there would be 1 times whatever C is, so 4A equals C. See if we can do the same thing for hydrogens and oxygens. If you want to pause it, you could have a go at that. So hydrogens, you're going to have A times 10, and then on this side you're going to have D times 2. And oxygens, you're going to have 2 lots of B on the left, and on the right you've got 2C plus D. Now at this point you might be thinking, well, I can't really solve any of this, what's the point of that? Now, because this is all just a ratio, the next stage here is you literally just pick a letter and put it in as 1, because then you'll get 1 is to something, and that's how you get ratios. So just arbitrarily I've put in A equals 1, but you can choose anything. So I'm sure that your algebra is strong enough that you can probably solve that. So feel free again to pause it, solve it. So what you're going to do is this. Obviously, if A is 1, 4 times 1 is 4, therefore C must be 4. Using equation number 2, you've then got 10 times 1 is 10 equals 2D, therefore if you do 10 divided by 2, D must equal 5. And finally, last one, all right, you can obviously put 2B equal to 8 plus 5 using your previous answers, and that will give you 13, so therefore 13 over 2 is 6.5, which of course we discussed on the previous slide is perfectly fine, giving you an overall equation looking like this, which is exactly the same as it was before. Now again, you might think this seems a little bit long-winded, but this method will always work. With the more complex examples, which you'll see on the A-level equation sheet, you might well end up with some simultaneous equations. Now, you may be okay with that, or you may not be, but it still may be quicker than trying to just do it by trial and error.